In this video, we will use the solubility product constant to determine the solubility of lead 2 bromide, which has a KSP of 8.9 times 10 to the minus 6. We will do that in part A in pure water, and then in part B, we will do it in the presence of 0.20 molar potassium bromide solution. This is nothing more than potassium bromide is potassium ion and bromide ion because it's soluble in water. And then finally, we'll do it in part C in the presence of lead 2 nitrate. Remember, all nitrates are soluble, so this is nothing more than lead plus 2 and nitrate. So the common ion here in part B is Br minus, whereas the common ion in part C is lead plus 2. So how will that influence the KSP reaction of lead 2 bromide? Remember, lead 2 bromide is what we call a sparingly soluble solid. It has a KSP denoted there as 8.9 times 10 to the minus 6. The first thing you want to do in any of and all of these types of KSP problems is write your KSP expression that defines this equation. So the sparingly soluble solid of lead 2 bromide, lead is a transition metal, so it's lead 2 bromide, is at an equilibrium with lead plus 2 and Br minus. We have to balance this equation. So in order to do that, we will put the stoichiometric coefficient of 2 by the Br minus. So the KSP is 8.9 times 10 to the minus 6. And so that's a very small number. So the equilibrium is primarily shifted to the left-hand side, to the side of the solid. Very little of it is going to go to the right-hand side, to the side of lead plus 2 and Br minus. That magnitude of 8.9 times 10 to the minus 6 tells you that the equilibrium primarily favors the solid or the left-hand side. So we will do our ice table, and instead of X, we will use S. The Br minus is 2S, remember, because it's 2 moles, and the KSP expression is solids over, the KSP expression is products over reactants. And don't forget to raise the Br minus to 2. The law of mass action is that you have to raise it to the stoichiometric coefficient, and for Br minus, the stoichiometric coefficient is 2. So plugging in those values, we will get S for Pb plus 2 and 2S for Br minus. We have to square it because that is what the equation tells us for the law of mass action. That whole thing is equal to 4S cubed, and 8.9 times 10 to the minus 6 is our KSP expression. So we have to solve for S. S, again, is solubility. So it's going to be 8.9 times 10 to the minus 6 divided by 4. And we'll take the cube root of it. Another way to do it is by taking 8.9 times 10 to the minus 6 divided by 4 and raising that whole number to the 1/3 power, raising that whole fraction. So those are essentially the same expressions. They'll give you the same answer. So doing this on our calculator, we will see here that that is the x square root. So you can do a cube root or fourth root. It's above the caret sign, so you have to hit shift. So it's going to be a cube root. So 3, shift that cube root because it's 3. If it's going to be a fourth root or a fifth root, you'll do 4 or 5. And then we'll put in that fraction. I like to put in parentheses 8.9 times 10 to the minus 6 divided by 4. Don't forget to close those parentheses, and you should get an answer of 0.0131. Here you want to put in the units. The solubility is in units of molar, which is moles per liter. So 0.0131 is the solubility of lead 2 bromide, lead bromide, in pure water. So what is the solubility of the ions? Individual ions is our next question. The solubility of lead plus 2 is S, which is going to be simply 0.0113 molar. The solubility of Br minus, remember, is 2S, not S, but 2S. So the solubility of that is going to be 2 times 0.013 molar, which is nothing more than 0.026 molar. So those are the answers for part A, the solubility in pure water. Now in part B, it's asking us not in pure water. We're going to take this solid and dissolve it in 0.2 molar potassium bromide. So what is 0.2 molar potassium bromide in part B? It is nothing more than potassium ion and bromide ion. And you can immediately see that that bromide ion that you dissolved it in is a common ion, and it's going to shift the equilibrium. The common ion effect tells us that the Br minus will shift the equilibrium. Just again, using Le Chatelier's principle, it's going to shift the equilibrium towards the formation of towards the formation of the solid. So once again, we're going to write our KSP equation for PBr2 solid. It's at an equilibrium between Pb plus 2 aqueous and Br minus. And to balance this equation, we will need two Br minuses. So it's going to be plus S plus 2S, but the Br minus here is actually coming from the 0.2 molar. So don't forget, you have this solid dissolved in potassium bromide. The Br minus is actually 0.2 molar. Remember, potassium bromide is potassium ion plus bromide ion. So that equilibrium is really going to be influenced by the presence of the Br minus, whose concentration in part B was 0.20 molar. So the Br minus concentration is not just 2S, which is coming from the KSP moving to the right-hand side. The concentration of Br minus is also from the 0.20 molar Br. So Le Chatelier's tells us that this reaction is going to shift towards the left, towards the formation of the solid. That's where the left-hand side of this equation is. And the common ion effect really tells us in these types of problems that you're going to get more precipitation. You're going to get more precipitation and less ionization, less formation of ions, more formation of the precipitate, as the reaction counterbalances the effect of the common ion. So we will write our KSP expression. It's going to be Pb plus 2 times Br minus. Don't forget to square it. Once again, when we put in our terms here for Pb plus 2 being S and Br minus being 2S plus 2O, we have to square that entire term. One thing is the primary driver, Br minus, is the 0.20 molar. Very little of the Br minus is coming from PbBr2 going in its equilibrium form, because the KSP is so small, 8.9 times 10 to the minus 6. Because the KSP magnitude is so small, very little of it is moving to the right-hand side. Most of the Br minus in this equation is coming from the 0.2 molar Br minus from potassium bromide. So we can make the assumption that Br minus, its concentration is 0.20 molar. So very little of it is going from the KSP reaction. Most of the Br minus is coming from the point. So here we can solve for S, and we will square root that entire expression to get S in units of moles over liter. The answer here is 0.000. That's 3 zeros, 223 M, big M. So notice what's happening here. Comparing this answer to part A, which was in pure water, we got an answer about 0.013 molar for solubility, and in the presence of the potassium bromide common ion, the solubility goes down. That is what is to be expected. More solid formation, more formation of the PbBr2 lead 2 bromide, more of that as a solid. It will enhance the precipitation. And again, that is just simply Le Chatelier's principle at work. So part C now, as we finish up this problem, is looking at it from lead to nitrate, which is lead plus 2 and nitrate ion. All nitrates are soluble, so that will be a source of the common ion lead plus 2 that will contribute to the equilibrium of the KSP. The lead to nitrate is lead plus 2 and the nitrate ion. We will write our equilibrium expression that defines the KSP for lead 2 bromide. Lead 2 bromide because lead is a transition metal, so we have to designate the charge. Br minus is plus 2S because of the coefficient of 2. The solubility of lead, S, is going to be S from the KSP reaction moving to the right, but also the concentration of lead will be the 0.20 molar contributed by the lead plus 2 in the lead nitrate. Plugging our values in, the lead plus 2 is 0.20 plus S, the Br minus is 2S, and that goes as whole square. We will make our assumption now that most of the lead plus 2 is coming from the 0.2 molar lead 2 nitrate. So S is very small Again, the KSP is so small that very little of it is going to the right from our KSP equilibrium. Most of the lead plus 2 is coming from the 0.2 molar lead 2 nitrate. That's the primary driver of the Pb plus 2 concentration in this problem. So our assumption is S is going to be small and the lead plus 2 concentration is 0.20 molar. Even though S is small, we have to still solve for S. Essentially, that is what this problem is telling us, to solve for S. It's just a small number. So 0.20 will be our lead concentration, and 4S squared is going to be the S that we will need to solve for. So isolating and solving for S, it's going to be 8.96 times 10 to the minus 6, 8.9 times 10 to the minus 6 divided by 0.2 times 4. We will square root that whole expression to get our final answer. Don't forget the units here are going to be molar, moles over liter, which is nothing more than big M. Solving for S on my calculator, getting a value of 0.0004011 molar. Again, the solubility of S of lead plus 2 and Br minus have gone down significantly in the presence of the common ion. Solubility of Br minus is going to be 2 times that S, so it's going to be 0.000022 molar.